afternoon, everybody. Thank you very much for the wonderful introduction that you made. And it's very nice to see all of you here. Thank you very much, sir, for all of you for coming. First of all, let me welcome you to this facility, the Geo World Center, which in my opinion is going to be here for a very long time and be a beacon for intelligent buildings that are to come. This we expect to be the benchmark of future intelligent buildings. I'm not saying there will be no better buildings made than this, but this will be a benchmark. So just to start our presentation, I will take you through a little of a small corporate film to show you what you are going to get here in this particular installation and what we have created in this. I will run this out. It's not coming here. Sound.
The future awaits you. Ready?
Enjoy the short film and then we'll talk about it. This is an open source data available. Anybody can see it on YouTube. So there's no privacy violation here. Banquet Hall that is there, a 3,000 square meter single hall. We have a facility that can dish out 18,000 meals a day, 9,000 for lunch, 9,000 for dinner.
Where do you want to go from here?
Kitchen, in-house facility, in-house laundry, everything there. This film has been shot on site. So this is not an animated or digitally modified film, this is on site. We have 3 theatres, an experimental theatre of 150 seats. This is the 2,000 seat theatre, the Grand Opera style theatre. And we have a 250 seat small theatre.
What are you waiting for?
This is the live Grand Theatre shot. We are the world's largest guest elevator, 14-ton capacity. This is the musical fountain, called the Fountain of Joy, that is dedicated to the city of Mumbai.
Welcome to the Geo World Centre, where we bring the best of India and the world to you.
My chairperson, please. Thank you very much. Now, since we have seen what kind of a facility we have created here, let's look at what we have gone through and what we have installed here to make this what it is. In principle, this is we call it an intelligent building by all sense, because we have tried to install a large amount of intelligence into it by way of equipment, devices, systems, applications, and so on and so forth. So let me take you through a small journey of how buildings became intelligent, because I am a history buff. I like how things started and how it has evolved as it is today. Long time ago, what did an intelligent building mean? It meant nothing but some kind of systems that are there to control repetitive processes. I think from there started one of the first requirement to control heating in buildings. That is when heating was being done through boilers. And we all know that the first control device that normally came out was basically a thermostat. So one such intelligent thing that is there, which really tempted the human mind, was to control everything. So that is how we brought in this particular device. Early features of an intelligent building were, we used to have the Vastu Shastra in buildings since Vedic times. We had understanding on incorporating of climatology and seasonal impacts to make habitation comfortable. We had thermal modeling, which is a modern concept now, but the Vastu Shastra took a lot of significance when they did thermal modeling to understand from which side the sun would come, which side the wind would blow. Then controlling simple physics like heating, cooling, and fine tuning. So the journey started, in my opinion, this is what history says. 1830, Scottish chemist Andrew Roux developed the first thermostat to regulate temperature in textile mills. On 24th July 1883, Warren Johnson got the patent for electric thermoscope in Milwaukee. He did this basically, he started using this to control the temperature in his, he was disturbed by the janitor coming and checking the temperature with a mercury thermometer in his classroom. So let's do something. So he created a thermostat, would put the fire on, would allow the water to come in the pipe and put coal into the furnace. Albert Bush, American inventor, invented the electric thermostat and patented the design in 1886. So literally control started from those days. That's how buildings started becoming intelligent step by step. In 1906, Mark Honeywell, after Booth's death, purchased Booth's patent and developed the first programmable thermostat. It's 1934 that we had the first programmable thermostat. Later in 1934 came the thermostat with an electric clock, that is what we call it. We all know the two names that are here, Johnson and Honeywell, what they are today. They are the giants in control systems today. This is for the trivia. This is the project that we are talking about. This is the magnitude of this project. We are talking about 7 lakh square meters of development, roughly 76 lakh square feet of development under one roof. This is an 18-acre plot taken on lease from MMRDA, and we have got these amenities in a broad sense here. We have got a convention center where we are all here. This is one floor of the convention center. Literally the other floors of it have not been used. You're using a little during the lunchtime, and there are some meeting rooms and other things. But on the third floor we have a banquet hall and the flex halls. This single hall is a 1,50,000 square feet hall with a 70 meter span. Then we have a 3 lakh roughly parking space, out of which 2.5 lakh square meters is used for parking, 5 levels of parking. We can house about 5,000 cars and about 500 two-wheelers. This is just, this is a huge mixed use development that we have. We have offices, we have retail, we have service residences, we have a clubhouse, we have a cultural center, we have a convention center. General features, what we expect in an intelligent building is connecting various building systems, connecting people and technology, filled with intelligent sensors, system integration platforms, ability to control either from a remote or in situ location through command centers. We do have a dedicated integrated command center where every service in this building, in this whole 76 lakh square feet of development can be monitored and controlled. So that's why we call it a little intelligent. Unless these buildings have the monitoring systems which are listed here, a few of them I have listed, the major ones, the building is not going to be intelligent because the systems will not be there. You may talk about it, you can't put the devices, you can't put the systems in. These are some of the systems that we have. In addition to this, there is one more in the fire detection that care has been taken. We have got a VESDA system, very early smoke detection apparatus. We all know what it does. For those who wish to know, it's a two-stage. In the first stage, it filters the dust particles out, and in the second stage, through a laser, we cross-check the content of smoke in it. It's a very early detection system. Since we have such high ceilings, by the time the smoke detector or the heat detectors operate, it may be too late. So the very early smoke detection apparatus is installed in this whole building, especially the convention systems and the public areas. What are the objectives that we have gone through during the design stage for this particular building? And we all expect this in some form or the other. We want the building to be automatic in every respect, no human intervention, reduce manpower, reduce capex and opex compared to non-intelligent buildings, shut down to cease due to failure. We don't want any failure, we don't want any shutdown. So we emphasize on prevention rather than correction. Building to be futuristic, it's an expectation, must dictate a high rental or sale price for the owners. Whoever is developing wants his building to give him good returns. Today, intelligent buildings, we use a combination of all this: computerized maintenance management systems, building automation systems, smart building technologies, and data analytics. Latest expectation and requirement during COVID has thrown few more challenges. I think the industry has adopted to it very well, and we have been able to meet the requirements of the public and the health authorities and the statutory requirements, whether it is in contact, non-contact systems. It has been a success. We all realize the biggest guzzler in any building is energy. This building is no different. We have given a lot of emphasis on energy monitoring, energy control, energy consumption reduction, indoor air quality, natural lighting, optimized condition. We'll just go through a few of them and understand how we have taken the philosophy in getting this building designed, which helps it to be intelligent. These are some of the salient features that I would like to bring to your notice. In addition to traditional MEP, we have got a plethora of advanced systems installed on this building. The approach we have taken is the PID approach, which is the proportional integral derivative system that is adopted. We have the machine learning, which goes on hunting and observes how equipments are performing and keeps correcting and gives feedback and tells us what is the pattern in which the equipments are working and what it is. Efforts to reduce the system lag and receive real-time responses from the equipment in the system based on demand. This system is sensitive to demand. There is no fixed capacities installed which will run. These are all variable and it will respond to demand. If the demand increases, it will go to its next level and will start performing. Demand reduces, energies will start reducing, consumptions will reduce. We have intelligent in terms of basically the HVAC system, which we know is one of the major consumer of energy, electromechanical systems next, lighting systems, ELV system. Just a small information, this whole facility has a 60 megawatt connected load. So we are handling a large amount of energy that will be consumed when this building is fully operational. We have ensured that the maximum demand does not go beyond 30 megawatts. Connected load is 60, but we ensure that the performance with its diversities and other things designed in it, this does not go beyond 30 megawatts so that our power bills are under control. What have we done for that to ensure that it happens? We have got chiller management system. We have over 10,000 tons of air conditioning installed. This I am talking on the high side. I am not talking on the low side. Add another 30% on the low side, that's the installed capacities. On the high side, we have 10,000 tons. This is like a district cooling plant that is running. So we need to manage the energies very well. What have we done to do that? We have not gone with the traditional approach. We have gone in with a high delta approach, reduce the GPM requirements, which reduces the movement of chilled water in the system. So we reduce a lot of energy costs there in pumping costs. That's where we start because this is a huge area where the energy is consumed. We have VFD on chiller motors, which reduces my starting current drastically and saves about 1,200 kilowatts on my maximum demand. Just the VFD chillers, the VFD on the chiller motor. We have about 750 AHUs, 200 FCUs in these ranges. We have jet fans, 900 of them in the basement parking. We have adopted MERV 13 as our standard here for filtration. We have not gone with MERV 8. It helps in trapping smaller particles up to 3 microns and reduces our housekeeping costs to a great extent, improves the indoor air quality with particle size. For all who wish to know about MERV, it is basically an adapting value, efficiency value, minimum reporting efficiency value. That's the filtrations which we have considered. In basement ventilation, we have a 4 megawatt load connected, so we need to monitor that load also. That's also a big power guzzler, which is covering about 2.5 million square feet. We have designed for a peak load of only 300 kilowatt here. Though the installed capacities are there, it is in different zones. These are based on maximum 4 hours a day of working, CO sensor based designs. Each CO sensor covers about 300 to 5,000 square feet depending on how they are located. Works on a principle of average value of CO sensor in a fire zone, PLC for adjusting and altering the RPM of the motors or the fans. This is the important area that we have worked on to make this building a little intelligent. We have gone on CO2 sensors for demand-based TFA ventilation. the CO2 is sensed and only on demand fresh air is added. If I continually start putting a constant amount of fresh air, we know it adds to its treatment. There's a cost that goes into its operation with so much of air. Then we have fresh air management, which we have done. Here, basically, the return air is constantly monitored, and then we ensure that the air is properly pumped in. In the basements, we have CO content monitors, which help you on this. We have two-way valves. We have not taken the standard valves. We have got pressure independent control valves, which helps in balancing the system. All motors above 2 kilowatts have got VFD drives, which saves about 35% of our power. Lighting and control systems, everything is dially controlled in the front of the house. Full occupancy, 100% lighting. No occupancy is just 20%. We have an electrical consumption load of 0.06 watts per square feet on this building. That's a benchmark that we have, which we need to monitor. All JDSP lights are LED lights. There's dimming control facility, program, scene setting, everything there. Thermally insulated walls, roofs, special glazing for high performance all around. High efficiency motors used, 75 to 82% performance efficiencies. Bus ducts used, no cables to a great extent, which reduces the losses. Open access for power, which is permitted now, reduces our cost on buying power. Destination control elevators, which is a normal feature. Proximity sensor based escalators. They don't run at full speed at all times. They're all proximity sensors there. Hydropneumatic system, which is a standard feature. This is an important parameter that we have been able to establish. JWC consumes 37% less energy than an ASHRAE building. Modeling is in this manner. This is 37% less power consumption. I think this good applause should go to the designers of this building and the owners who have had faith in implementing this. Our BOD of our recycled water, that the expected is only 5 ppm BOD. We have used BIM a lot. Right from the beginning stage, we have used BIM. I cannot explain the kind of benefits that we have gone. It's beyond measure, because today I have a digital record of this building. I have a digital map of this building. I have linked it with asset controls. This is how we have done coding, just for an example. Then this is how the processes have been used, different stages that we have taken. Design model, starting at the design phase, model reviews, spatial coordination, asset data. Then we have the design phase. Then we have the construction phase, in which all these parameters are touched. Asset data checked and developed at the end, before which we don't go into the next stage. This is the commissioning stage, where we have the BIM process and activation stage. We have the final inspection, asset data finalized, final formatted, final data load to asset management software. Integrate the BM model with EAM software. We have done this. These are the kind of softwares that we have done. The result is we have an as-built model. It is now relevant for the life of the facility. Visualization tool embedded within asset management software. All work can be verified, redone, tracked. Benefits of operating with BIM. The consistent, accurate information, effectively planned for future and the next life cycle. These are some photographs of the facility. This is the theatre that I was referring to. This is the lobby that you are all entering through, a grand 3-level lobby. And this is the drone shot of the installation. This is the banquet hall and the flex hall, which is at the higher floors, which we have not visited. So I'm just showing you a photograph of this particular thing. Thank you very much for this opportunity. Hope you enjoyed having a look at the building.